So now students, here we are going to learn about the transient analysis of RL circuit using Laplace transform. Okay, so here you are going to learn about one of the advantage of Laplace transform, and here's in one of the main advantage in our circuit in this subject. The main advantage of Laplace transform is that you can actually apply transient analysis of any circuit. Okay, that is one of the advantages of this, because under normal condition, if you are not using Laplace transform and when you are applying transient analysis to RL or RC circuit, right, or usually it involves some kind of a differential equations in which we have to find both the particular solution and the homogeneous solution, right? But here, since now we have learned Laplace transform, so finding the transient analysis of any circuit using Laplace transform will become very easy for you. Okay, and that is what we are going to learn here. Here we are going to learn about the transient analysis of a circuit that consists of only of a resistor and an inductor, series resistor and a series inductor. Okay, so before moving forward with this, I want you all to know how to find the inverse Laplace transform. Okay, that most of you might have already studied that is, you should learn, or if you are not, then you should learn how to find the inverse Laplace transform of a function and through partial fraction. That is the only method you need to study for this subject. Okay, so I hope all of you know that method. If you don't know, I suggest you all study that before continuing this video. Otherwise, it will be very difficult for you to understand this. Okay, not in the sense of difficulty, it will be very difficult for you to solve the problems. That is why. Okay, so that is what. So I hope so. It is expected for all of you to revise that portion. Okay, you can refer to any of your previous semester maths class or anywhere in how to find the inverse Laplace transform using partial fraction method, because we need that in order to find our solution in this coming chapter. Okay, in this complete videos of this chapter, we'll be using partial fraction method, and also we'll be doing problems. So from there also you can also study how to find the inverse Laplace transform using partial fraction. Okay, so that is expected of you. And another thing that is expected from you is that you need to learn you need to know by heart all the Laplace transform functions. Okay, if you are unsure about that also, I suggest you all to refer to my previous videos and study each one of those formulas. It's very important, because once if you know all these formulas, then finding the answer will become very easy for you. Okay, so it's very important that you know both the properties as well as you know all the functions. Okay, before moving on to this chapter. So now let's move on to this chapter. So here what is going to take place is that in this RL circuit, there consists of a switch. Okay, let me draw a switch. Okay, it consists of a switch, and it consists of a series resistor with an inductor. Okay, a series RL circuit. This is called a series RL circuit. It is R and L are in series, and the circuit has a voltage source plus minus. Okay, and I'm going to name this voltage source as V of t, small letter v of t. The value of this resistor is R, and the value of this inductor is L Henry, and this is a switch. Okay, as I said, this is a switch. I'll write a switch. Okay, and this voltage is generally a current called as I of t. Okay, so this is basically called as the RL circuit. Okay, what is the use of the switch? As I explained in the previous video, what is the use of the switch? We all know that when you are going to apply Laplace transform to the circuit, right, we need to know the initial value condition, and the value of the initial conditions depends on the position of the switch, or the position in which the switch remains there for a long time. That position is actually what you call as the steady state condition. Okay, so by looking at the position of the switch, whether it is in the on position or on the off position, depending on whether it is open or whether it is in the closed position, we look at which condition the circuit is, and then from there we understand what is the steady state condition, and we find the initial value current of the inductor. Because you remember, when you are finding the Laplace transform of the inductor, what happens is that the inductor changes into an impedance called as Ls along with a negative voltage called as Li of 0, right? So if you want to find the I of 0, then you need to apply, when you need to understand where is the steady state condition, okay? But now in this derivation, I'm going to assume that the initial conditions are all 0, okay? I'm going to assume that is, here in the circuit, the switch is closed at time t is equal to 0. That is, at time t is equal to 0 only the circuit will turn on, right? Because at t is equal to 0, the switch will come into the on position. So therefore this voltage will generate the current and there will be a current flow in the circuit. If the switch was open, then there won't be any current, right? So the current across these two elements will become 0. So that's what I'm saying. The switch is closed at time t is equal to 0. That means at the starting point is that the switch is closed, not before that. And the initial conditions are 0, okay? The initial conditions are 0. So in that case, now when I'm going to apply the transformation of the circuit, what is the transformed circuit of this looks like? Hence the transformed circuit looks like this. That is, the switch is closed, okay? So it is closed. So the transformed circuit looks like this, okay? We have over here a resistor whose value is R. We have over here as a voltage, the same voltage, okay? Plus minus the same voltage, but this time we say this is capital letter V of S, where capital letter V of S is the Laplace transform of small letter v of t, okay? That means this is voltage source, the Laplace transform of this voltage source, okay? And also there is a current, okay? The current is I of S, capital letter I of S, where I of S is the Laplace transform of this small letter I of t, okay? So everything will be in terms of Laplace transform. This will be an inductor, okay, and the value of this impedance of this inductor is Ls, okay? Actually, if you remember very correctly, it is not supposed to be inductor, it is supposed to be an inductor with a negative voltage, right? If you remember, that's how we studied actually, right? It should be an inductor with that negative voltage. But here, since I have already mentioned that the initial conditions are 0, then I of 0 is 0. Therefore, the value of this voltage is 0. So if this is 0, means it is short. That is why it is complete over here, okay? This is what I meant, okay? So that means, in other words, what it means is that there is no voltage source. If the initial conditions are 0, then the voltage source is, then every inductor will be replaced by Ls and every capacitor will be replaced by 1 by Cs. That's all. There will be no extra voltage source for both these elements. That's all, okay? So now I'm going to apply Kirchhoff's voltage. This is very simple, right? So now I'm going to apply Kirchhoff's voltage law. I'm going to define the equation for the circuit. So what you get is, you get V of S is equal to I of S into R plus Ls, right? This is the equation there. This is the mesh analysis of this equation, right? V of S is equal to I of S into R plus L of S, where R is the impedance across this resistor and Ls is the impedance across the inductor. So that's why this is I of S into R plus L of S, okay? Now this can also be written as, I can say that I of S is equal to V of S by R plus Ls, okay? Now from here onwards, you need to understand what we are doing over here. What we are doing over here is, you might be trying to find the current across the inductor or the current across a resistor. Both of them, the value is I of S, okay? And also you may be trying to find the, suppose sometimes they won't ask you to find the current. Sometimes they will ask you to find the voltage across the element. Sometimes they will ask you find the voltage across a resistor. In that case, you already found what the current is, right? This is the current. So what is the voltage across a resistor? The voltage across a resistor, in that case, you should all know that the voltage across the resistor is equal to, that is nothing but, we all know Ohm's law, that is I of S into R. I of S into R, right? So therefore this is equal to, and what is I of S? This is I of S. So therefore this is V of S by R plus Ls into R. Okay, this is the equation. This is for voltage across the resistor. And also now if you are trying to ask you to find what is the voltage across the inductor, then you should be able to say, that is the voltage across, see for that is what is the meaning of voltage. That is, if you want to know the voltage, you need to know the current and you need to know the impedance. So what is the current through the inductor? The current through the inductor is I of S. So it is I of S. And what is the impedance of the inductor? The impedance of inductor is Ls. So this is the voltage across the inductor. That is I of S into Ls. And what is I of S? This is I of S. V of S by R plus Ls into Ls. Okay, this is the voltage across the inductor. This is the voltage across the resistor. And this is the current across the resistor or the current across the inductor. Okay, so this is how the question will be asked. They will ask you to find one of these elements. They'll ask you to find the current across an element, or they will ask you to find the voltage across the element. Both of them, the answers somewhat are all proportional to each other, because if you need to find the voltage across a resistor, you need to first find the current, and then you should multiply the current with that resistor. Likewise over here also, if you want to find the voltage across the inductor, you need to find the current through the inductor, and then you need to multiply that current with the impedance of the inductor, which is Ls. And that is how we find this equation. Okay, so I'm just telling you how the questions should be asked. Okay, and then what you need to do is you need to find the inverse Laplace transform. That is why I said that you need to learn the inverse Laplace transform, because otherwise by applying that only you will be able to find the voltage and the current values in terms of time. Okay, and usually the method we use over here is this method, that is the partial fraction method. Okay, so now one more thing I'm going to tell you. Okay, it's not just one more thing, there's a lot of things I need to tell you over here. That is, you see, let me write that equation again, the equation that we just found out. That is, this is I of S into V of S by R plus Ls. Okay, this is the equation you have written for the RL circuit. Okay, now I want you all to pause everything, to stop everything and simply look at this equation. Okay, and I need to give you a very important concept that you're going to need to apply in all these problems, a trick, a very neat trick of how to find the inverse Laplace transform. You see, you cannot apply the inverse Laplace transform of this equation directly. See, because you have not studied any single formula that looks like this. I am talking about the denominator. I want you all to look at the denominator. Look at the denominator, R plus Ls. If you look at all your previous formulas that you have studied before, all your previous formulas, it will either be 1 by S, or it will either be 1 by S plus A, or it will either be 1 by S minus A, or it will either be what else? It can either be S by S square plus omega square, or it can either be omega by S square plus omega square, or it can either be S by S minus A or S plus A the whole square plus omega square, or it can either be S by S minus A the whole square plus omega square. I'm talking about the denominator. Look at the denominator. The denominator can either be in terms of S, or it will be S plus A, or S minus A, or S square plus omega square, or S square minus omega square, or it can be S plus A the whole square plus omega square, or it can either be S plus A the whole square minus omega square, and so on. You see, so this is how the denominator looks like, the denominator which you have studied, that is the denominator of the Laplace transform formulas of which you have studied, right? Now what you need to do is, when these kinds of questions comes, you need to modify this equation that you're seeing here. You need to modify this equation in such a way that it looks like in terms of the denominator of the formulas which you have studied. That is what you need to do over here. That is, you need to change this equation in such a way that it should look like the formulas which you have studied. For example, okay, we all know that the Laplace transform of e raised to minus 80 is 1 by S plus A, right? So which means if you see 1 by s plus a anywhere, if you see 1 by s plus a anywhere, you can immediately understand that it is the Laplace inverse, or it is the Laplace transform of e raised to minus at, right? So look over here now. Here you don't see any s plus a, but what you can see here is r plus ls. So what you need to do is you need to make this thing look like this one over here. And how do you do that? Very simple. That is a tactic you need to. That is a secret I'm trying to tell you. That is what you need to do is you need to change this by simply taking the L common. So if you take the L common, then the coefficient of this s becomes 1 plus r by L. You see? You need to learn to write this equation in this format. That is, it should either be, why did I write this in this format? Because this format looks like this. So that when you are going to find the inverse, it will become very, very easy for you to find the inverse, since you already know the formula of this. So I want to make this equation look like this. So that is why I took the L common out. You see, in all these cases, if you look very carefully, the coefficient of s is 1 itself. So which means wherever you see over here as n, wherever you see s or s square, make sure that the coefficient is 1. And how do you make the coefficient 1? Is by simply taking that particular value common. Okay, this is what you need to understand about this condition. Okay, and this is the technique you need to understand for all the coming problems. This technique, that is, you need to learn. This is the basic thing I'm trying to tell you. That is, you need to learn how to convert every denominator that is looking somewhat like this into a denominator which is looking like any one of these formulas. Because unless and until you get any one of these formulas only, you can actually find its inverse. Okay. So I found the value of I of s. So this is my equation of I of s. Okay. So this equation is it's actually incomplete. So which, according to this equation, if you need to find I of s, then you need to know what is V of s. You need to know what is V of s. And what is V of s? V of s is the Laplace transform of V of t. Okay. And now depending on the value of V of t, the value of V of s will change. So that means depending on what the value of V of t will be. Okay. So in your syllabus, you need to study V of t. You need to study V of t equal to, if it is equal to an impulse signal. That is first case. Okay. That is first case. If V of t is equal to del of t, that is one case. That is case 1. Second case is if V of t is equal to a step signal, or this is a unit step signal. V of t is equal to u of t. Okay. So let me take it step by step. So this is V of t is equal to u of t. Another way of writing, another signal is if V of t is equal to a pulse signal. A pulse signal is this equation. That is u of t minus u of t minus a. This is called as the pulse signal. That is, this signal is a pulse with a duration of a seconds. Small letter a seconds. Okay, this is another way, and the other way will another case will be if V of t is equal to e raised to minus 8t. Okay, if V of t, that is another case, and the other case will be if V of t is a sinusoidal function. Sinusoidal function means it can be a cos omega t or a sin omega t. I'm going to assume it is a sin omega t. Okay. That is, these are the different values of V of t which you will get in your question. And depending on the value of V of t, okay, depending on the value of V of t, the value of the Laplace transform of V of t, that is V of s, will change. Okay. You all know what is if V of t is equal to del of t, then what is V of s over here? V of s is the Laplace transform of del of t. We know that the Laplace transform of del of t is 1. So therefore, V of s is equal to 1. If V of t is equal to u of t, then the Laplace transform of u of t is 1 by s. If V of t is this pulse signal, u of t minus a, then the Laplace transform of V of s is nothing but 1 by s minus e raised to minus as by s. Okay, and if the V of t is equal to e raised to minus at, then the Laplace transform is V of s is equal to 1 by s plus a. If V of t is equal to this equation, then V of s will become a into s by s square plus omega square. So depending what your question is, okay, depending what is your v of t, correspondingly your v of s will depend on that Laplace transform. So this depends on what kind of the signal is your voltage, whether it is a unit impulse signal, or whether it is a unit step signal, or whether it is a pulse signal, or whether it is a exponential function, or whether it is a sinusoidal function. Sinusoidal function means this a represents the amplitude and this omega represents the angular frequency. So let's analyze every equation in this circuit only. Okay, I'm just going to show you how. Actually, the thing about this is that it will be much more easier for you to do the problems than the derivation, but I want to show you how we are doing it. That is why I am taking this much time in solving each one of these equations. Okay, first let me take the first case. The first case is if v of t is equal to del of t. Okay, if v of t is equal to del of t. So we already know that this v of t is the del of t is a unit impulse signal, right? So if v of t is equal to del of t, then v of s is equal to 1, right? That is if, okay, case 1, if v of t is equal to del of t, then v of s is equal to 1. If v of s is equal to 1, then how this equation will become? We all know that I of s is equal to v of s by L into s plus r by L. So this is nothing but v of s is 1, so this will become 1 by L into s plus r by L. You see, this is the equation. So in that case, we all know what is I of t, right? I of t is nothing but 1 by L into the Laplace inverse of 1 by s plus r by L. And what is this equal to? This is 1 by L into, and what is the Laplace inverse of this? It is e raised to minus r by L t into u of t. This is the answer. See, very easily I found out the answer of this equation, right? And here I multiply the answer with u of t to show you that this signal is from 0 to infinity. That is why we usually multiply our answer with u of t to show you that this is a unilateral Laplace transform, or the signal is a unilateral signal. That is why we multiply the answer with u of t. Okay, so this is, see, I found the Laplace transform of this, right? This is how we find the inverse. This is how we find the inverse Laplace transform. This is how we do the problem. That is, once when we understand how to transform this equation in this form, then it will become very easy for you to find the inverse. Okay, so this is when v of t is equal to del of t. Okay, now let me ask you, you know what is del of t, right? This is del of t. This is del of t. This equation right here, this is called as del of t, right? Now what happens if this del of t is being shifted? What happens if the del of t is being shifted? See what happens. Then what will be the signal? Okay, let's do that. We'll try everything. Okay, see, if del of t is being shifted, okay, give me a number. If del of t is being shifted by okay, let be shifted by capital T seconds, let's say like that. Okay, then what is the name of the signal? This signal is called as del of t minus t. This signal is called as del of t minus t. This t minus capital T, where capital T is the amount of duration that the signal has been shifted, which means the signal is supposed to be at the origin, but now it is being shifted by t seconds. That is why it becomes del of t minus t. So if v of t is equal to del of t minus t, okay, if v of t is equal to del of t minus t, then what is v of s? In that case, what is v of s? V of s is nothing but you simply apply the frequency time shifting property in this equation. So this equation will become, we all know the Laplace transform of del of t is equal to 1. So therefore the Laplace transform of del of t minus t is nothing but e raised to minus ts into 1, where this one is the Laplace transform of del of t. So therefore this is nothing but e raised to minus ts. See, this is e raised to minus ts. So we already know that the equation for I of s is v of s by L into s plus r by L, right? This is the equation we have studied. So therefore, if I substitute v of s over here, this will become e raised to minus ts by L into s plus r by L. Okay, so in that case, In that case, this can also be written, I'm going to write like this as e raised to minus ts, okay, e raised to minus ts into 1 by, I write over here L also, I can take L also common, so s plus r by L, okay. So in that case, how will I find my Laplace inverse if you see an exponential function? Very easy, right? Because this is called as time shifting property. That is, if the time property, if the time domain is being shifted, the frequency domain is multiplied with exponential function, or vice versa. If the frequency domain is multiplied by exponential function, then the time domain is being shifted. So which means here this being the exponential function is multiplied by e raised to minus ts, right? Capital T. Look at that, it is capital Ts, right? That is capital T is the shifted duration. How much it's being shifted, that is capital T. So in that case, I can say that I of t is nothing but the Laplace inverse of e raised to minus ts by L into 1 by s plus r by L. Okay. Or I can say I can take 1 by L common, right? I can take 1 by L common, and then I can tell you that this is nothing but e raised to minus ts into the Laplace inverse of 1 by s plus r by L. And then you apply the time shifting property. So we know what is the Laplace transform of the Laplace inverse of 1 by s plus r by L, right? That is e raised to minus r by L small letter t, right? E raised to minus r by L small letter t. So therefore, this is now being multiplied with this exponential function, that is e raised to minus ts. So therefore, it is 1 by L into e raised to minus r by L into t minus t into u of t minus t. See? This is the equation. Look over here and look over here. Here, there is no exponential function that is being multiplied, right? Why there is no exponential function is being multiplied? Because this unit impulse signal is not being shifted, right? It is at the origin itself. That is why there is no exponential function over here. And therefore, when you found the value of the inverse, you got a straightforward answer. Now look over here. Now this time it's being shifted. So since it's being shifted, the answer you will get over here is being multiplied with the exponential function. You keep the exponential where it is, and as usual you simply find the Laplace inverse of this. So when you find the Laplace inverse of this, you will get this, right? Then what you do is you apply time shifting property to this. That is, the time shifting property which depends on the value of the constant over here, and here the value is minus t. So you substitute every t over here, you substitute every t over here with t minus t. That's all. And that is how we find the answer. That is how we find the inverse. This is when the impulse signal is shifted. Okay. Now next I'm going to apply what happens if v of t is equal to u of t. What happens if this v of t is, say, u of t? If v of t is equal to u of t, then v of s is equal to 1 by s. Okay, this is a unit step signal, UNIT, unit step signal. Okay, now what happens? Now I'm not going to, suppose if it is not a unit step signal, what are you going to do? Suppose, okay, I'm going to draw a signal in which the amplitude is not 1, it is 5. Okay, then this is called as a step signal. Okay, that is the difference between a unit step signal and a step signal. In a unit step signal, the amplitude is 1. That is why it's called as a unit step signal. But if you simply say a step signal, then the amplitude can be any value. Okay, it can be any value including 1. So here if I say 5, then this equation, then this v of t, okay, suppose I'm saying it's 5 volt. So in that case, then v of t is equal to 5 u of t. This is the new, this is the equation of the step signal. Okay, 5 u of t. That is, you multiply that constant with u of t. That's all. Okay, so likewise, so step signal is also a unit step signal, because it is here, if the amplitude is 1, then this will become a unit step signal, right? Or if I say if the amplitude is a, in other words, if the amplitude is a volt, if the amplitude is a, then v of t is a u of t. Okay, then the v of t is equal to a u of t. So this is the equation of the step signal. If v of t is equal to a into u of t, then what is v of s? V of s is nothing but, we all know that a is a constant and the Laplace transform of u of t is 1 by s. So the Laplace transform of v of t is, v of s is equal to a by s, right? A by s. We already know that the equation for I of s, right? The equation for I of s is nothing but v of s by L into s plus r by L, right? This is the equation, right? So now we know what is v of s. V of s is a by s, so it will become a by L into s plus r by L, right? A by L into s plus r by L. Okay, so this is called as the equation. So now here you're going to apply the Laplace transform. Let me change this. I'm going to take L common, and this will be changing into a by s into s plus r by L. Okay, so now you're going to apply the inverse Laplace transform. You need to find the inverse Laplace transform of this equation by applying the partial fraction method. So by applying the partial fraction method, what do you get? You get this will change into 1 by L into, this will change, you need to separate this into two fractions. Okay, so this is so depending on how many fractions there are over here, okay, how many fractions they are, you need to split them into two terms. That means how many fractions are there, that many terms should be there. So here let me say I'm going to divide this term into a1 by s plus b1 by s plus r by L, where a1 and b1 are the coefficients which you need to find. Okay, and then you need to substitute that value over here. As you need to find, you can either use the cross multiplication method to find the value of a1 and b1, or you can simply substitute the value of the denominator of the equation into the corresponding value to find its corresponding coefficient. Which means, like, for example, if you want to find the value of a1, okay, if you want to find the value of a1, look at the denominator of a1. The denominator of a1 is s. So what you do is you remove s from this equation. Simply remove s from this equation and substitute the equation of s as s is equal to 0, right? Because with the denominator you need to find the value of s by equating the denominator to 0. So s is equal to 0, that is the equation. Therefore the value of s is equal to 0, which means if you want to find the value of a1, you first need to remove its corresponding denominator, that is the denominator is s. So you need to remove s from here, and after removing the s from here, substitute the remaining value of s with 0, and what do you get? You get a by 0 plus r by L. What a by 0 plus r by L is a L by r. Okay, like that how we find the value of a1. In the same way, the value of b1. How to find the value of b1? Look at the denominator of b1. The denominator of b1 is s plus r by L. If s plus r by L is equal to 0, then s is equal to minus r by L. So if you want to find the value of b1, first in this equation you first remove the denominator of b1, that is the s plus r by L. You remove the denominator, and the remaining value of the s you substitute it as minus r by L, and that's how you find the value of b1. Okay, I'm just explaining to you the partial fraction method. That's what I just did. If you have not understood also, it's okay, we'll be doing this by using the problems. Okay, so like that we find the value of this, and at the end of this what we do is we simply find the inverse. After finding the value of a1 and b1, we find its inverse. So what will be the inverse? The inverse will be 1 by L into a1 into u of t plus b1 into e raised to minus r by L t u of t. This is the inverse Laplace transform. This is the inverse Laplace transform of this function. That is, we all know that a1 and b1 are the coefficients, they are the constants. Okay, so now we need to know what is Laplace inverse of 1 by s, right? The Laplace transform of u of t is 1 by s, therefore the Laplace inverse of 1 by s is u of t. In the same way, the Laplace inverse of s plus a, 1 by s plus a is e raised to minus at, right? So therefore the Laplace inverse of 1 by s plus r by L is e raised to minus r by L t u of t. This is called as frequency shifting property, right? So in other words, I can now say that 1 by L into a1 plus b1 e raised to minus r by L t u of t. It is the is the current across the circuit. Okay. This is when the signal is a step signal. Okay. And remember the value of A1 and B1 that you see over here, the value of A1, the value of B1, the value of R, the value of L, all these values depends on the circuit. Okay. Depending on that, this values will change and this formulas will also change. Okay. This is just to give you a framework of how we are doing this problem. That's all. So this is when the signal is a step signal. Okay. Now if the signal is a pulse signal, okay, if it is a pulse signal, I had just simply wrote the formula of the pulse signal, but I didn't explain how you got this formula. You see, what is a pulse? Let me just ask you that. Pulse means this is the pulse. Okay, that is, it should have a finite width and should have a finite height. So this is a pulse signal. It starts, we are assuming it starts from 0 and it ends at, give me a value, I'll put it a small letter A. Okay. And the amplitude, you can make it, you can give an amplitude of your own choice. So let me put it as, what amplitude should I give? I'll put capital letter A. Just so you can understand. Okay. So this is called as the pulse signal. Okay. Let's make it unity. I don't want to make it more difficult. Okay. Let's make it 1. So what is the equation of this signal? This is V of t. Okay. So what is the equation of this? How to write the equation of this kind of a pulse? You need to learn to write the equation of any pulse signal depending on how the position of the pulse is. Okay. So you see over here, how do I write the equation of this? Okay. See, to understand that, you all know what is unit step signal, right? This is the unit step signal. There. I just drew the unit step signal. This is u of t and the amplitude is 1 and the time is t, 0. So this is called as the unit step signal. Now, if I'm going to shift this unit step signal, if I shift this unit step signal and I'm going to shift it by a seconds, okay, I'm going to shift it by a seconds, then how does my signal look like? It will look like this. That is, now the difference between this signal and this signal is that this signal is not being shifted. This is an ordinary unit step signal, but this is also a unit step signal, but it starts from a, or it's being shifted to a seconds. So the name of the signal is u of t minus a. The name of this signal is u of t. Okay, now I'm asking you, what will happen if I subtract this signal with this signal, or subtract this from this? Okay, that is u of t minus a. What will happen? What will happen if I subtract this with this minus this? What will I get? If I subtract these two, then what happens is that, you see, from here to here, the value of u of t minus a is 0. So what is 1 minus 0? It is 1. Okay, and from a to infinity, the value of u of t is 1 and the value of u of t minus a is also 1. So here also is 1, here is also 1, 1 minus 1 is 0. That means from a to infinity, the value of the difference is 0. So this is the pulse you get. That is, you will get this pulse when two unit step signals are being subtracted from each other. That is, one will be the normal unit step signal and the other will be its it will be its shifted version. That is why the equation of the pulse is given by u of t minus u of t minus a. That is why this equation is like this. Okay, that is why this is the equation of the pulse signal. That is, it's nothing but the difference between two step signals. Okay, and two step signals, and depending on the duration or the position of the pulse, the unit step signals function will also change. Okay, so this is the equation of the pulse signal. So if this is v of t, what is v of s? Then v of s is equal to 1 by s minus e raised to minus as by s. Or no need or, okay, it's 1 by e raised to minus as by s. Okay, so in that case, if this is v of s, we all know what is the current through the RL circuit. It is I of s is equal to v of s by L into s plus R by L, right? So therefore this will become I of s is equal to 1 by s, or 1 minus e raised to minus as by L into s plus r by L. That is after substituting the value of v of s. Okay, I get this. So if I take L common out, it will become 1 by L into 1 minus e raised to minus as by s into s plus r by L. Okay, this is how the equation looks like. Or I can write this as 1 by L into 1 by s into s plus r by L minus, this can also be written as e raised to minus small letter a 1 by s into s plus r by L. Okay, which means all you need to do is simply find the Laplace transform of this, and hence you will also find the Laplace transform of this. So what happens if I find the Laplace transform? That is nothing but 1 by s into s plus r by L. If you want, I will show you the Laplace transform of this. Okay, let me just show you how to find the Laplace transform of this. Okay, so here what is 1 by s plus r by L? So this is nothing but a by s plus b by s plus r by L. This is called as the partial fraction method. Okay, so I substitute the value of, so to find the value of a, I remove the denominator of a. What is the denominator of a? Is s. So I remove s from here and substitute the value of s as s is equal to 0. So when s is equal to 0, the value of a will become as value of a, or let me write like this so you will understand, that is 1 by s plus r by L when s is equal to 0. This is the value of a. What you will get? You will get 1 by 0 plus r by L, which is nothing but L by r. Okay, in the same way, if I want to find the value of b, what I do is I remove the denominator of b from here, and so if I remove the denominator of b, I'll get 1 by s. Okay, then I substitute the value of s as equal to s plus r by L is equal to 0. Therefore s is equal to minus r by L, so you get s is equal to minus r by L. So substitute the value of s is equal to minus r by L, you get minus L by r. So this is the value of a, this is the value of b. Okay, so in that case I can say that 1 by s into s plus r by L, right, is equal to L by r into 1 by s plus minus L by r into 1 by s plus r by L. So in that case I can now find the inverse, right? I can now find the inverse. So before finding the inverse, let me just write this whole thing what I just said over here. Okay, so therefore what happens over here, I of s, or if you want to find the inverse of that, is the Laplace inverse of 1 by s into s plus r by L. Let me write that. The Laplace inverse of this is nothing but L by r, the Laplace inverse of 1 by s minus L by r, the Laplace inverse of 1 by s plus r by L. And what is the L by r? What is the Laplace inverse of 1 by s? It is u of t. And minus L by r, what is the Laplace inverse of this? This is e raised to minus r by L t u of t. Okay, see, this is how we find the Laplace inverse. So now I'm going to substitute all these things over here. So over here, I of t is equal to 1 by L into the Laplace inverse of 1 by s into s plus r by L, which you have already found out over here, minus, and this is Laplace inverse of e raised to minus as into the time shifting, this is time shifting property again, right, 1 by s into s plus r by L. Okay, and hence you will get over here as I of t is equal to 1 by L, okay, into, and here you will get is, what is the Laplace inverse of this? L by r u of t minus L by r into e raised to minus r by L t u of t. Okay, minus now what is the Laplace inverse of this? Again, just like before, time shifting property applied to this, right? Time shifting property applied to this, and what is the value of the shift? It is minus 8. So time shifting property applied to this when the shift is equal to minus 8. So you will get, this is the equation, right? So let's see. you will get L by R into U of t minus a minus L by R into e raised to minus R by L into t minus a into U of t minus a. There you go. This is the equation. Okay. Here you can, if you can take L by R common, so if you will get, and 1 by L and L by R will cancel each other, so you will get 1 by R, and if you get 1 by R, you get the equation as 1 by R into, this will become 1 minus e raised to minus R by L t U of t minus, and here it will become again 1 minus e raised to minus R by L t into U of t minus a. There you go. See, again this equation will become more easier when you actually substitute the values of every one of them inside this L, R, A, R, L, this A over here, all these values, if you substitute, this equation becomes much more easier. This is just to show you how to do the analysis. So this is a pulse signal. Likewise, the same way when V of t is equal to an exponential function. If it is an exponential function, then V of s is equal to 1 by s plus a. It can either be a decreasing exponential function or an increasing exponential function. Okay, depends on the question. In that case, it will either be 1 by s plus a, or it can either be 1 by s minus a, depending on the equation. So in that case, again, we know that I of s is equal to V of s by L into s plus R by L, right? So in that case, again, the V of s, I already know it is this one. So therefore, this will become 1 by L into s plus a into s plus R by L. Then I find the value of this using, again, I find the value of this using the Laplace transform inverse. So that means I will go to use partial fraction. So this will become 1 by L into 1 by s plus a into s plus R by L. Okay, I'm not going to waste my time in finding the value. I hope all of you know how to do this question, right? Okay, this you need to apply the value of the partial fraction method, and then you need to find the value of a and b, and after finding the value of a and b, then I of t is equal to 1 by L into a into e raised to minus at U of t minus b into e raised to minus R by L t U of t. See, this is how we find the equation. Okay, or I can say this is nothing but 1 by L into a into e raised to minus at minus b into e raised to minus R by L t into U of t, where the value of a and b, you need to find the coefficients. A coefficient method of finding the coefficients is exactly before, that is, if you want to find the value of capital letter A, what you do is s plus a is equal to 0, so therefore s is equal to minus a. So if you want to find the value of this coefficient, you need to remove its corresponding denominator and substitute the value of s as small letter minus a. Okay, small letter minus a. Likewise, if you want to find the value of b, then you know that s is equal to minus R by L, right? Because s plus R by L is equal to 0, so therefore s is equal to minus R by L. So in that case, then you need to substitute. So in that case, s is equal to minus R by L, right? So in that case, what you do is you substitute that, you remove that denominator over here, remove this denominator from here, so it will become, this s will become minus R by L, and like that you can find the value of b. Okay, we will be doing this we will be doing problems based on this, and you will understand how to do it. Okay, so this is about the exponential function, and the last case is when it is an sinusoidal signal, that is a sine omega t. Okay, what if you get this? So in that case, then V of s is again same story. You need to know, in that case, V of s is equal to a into what is the Laplace transform of sine omega t? It is omega by s square plus omega square. So therefore, again, when I of s is equal to V of s by L into R plus, no, s plus R by L. Okay, s plus R by L. Now the value of V of s is this one. So you will get a into omega by L into s square plus omega square into s plus R by L. This is the equation you get, and what you need to do is you need to factorize this in this term, that is, this will become a1s plus a2 by s square plus omega square, plus this will become b by S plus R by L here, and here you need to find the value of A1 and A2 and B. These are the coefficients in order to find the equation. Okay, and you need to find the value of every one of these coefficients. Okay, to find the value of B is just a simple straightforward method, that is simply remove S plus R by L from this equation, remove that factor from here and substitute the value of S as S is equal to minus R by L. So from there you can find the value of B. But to find the value of these two coefficients, that is A1 and A2, that will be a little bit tedious. It's the only way you can find right now, the only way you can find is by applying the cross multiplication. That is simply cross multiplying each other and then equating it. You will find the value of A1 and A2. These are the coefficients. And once after finding the value of A1 and A2, okay, after finding the value of A1 and A2, what you do is you find its inverse. And how do you find the inverse of this? Before finding the inverse, let me rewrite this. I'm going to write this as like this: A1 into S by S square plus omega square plus A2 by S square plus omega square plus B by S plus R by N. Okay, these are the three equations over here. Okay, so in that case, you see, I know the Laplace transform of this, right? What is the Laplace transform of, what's the Laplace inverse of this S by S square plus omega square? It is sine omega t, right? But what about this? I don't know the Laplace inverse of this, because we all know that the Laplace transform is either it will be S by S square plus omega square, or you should get this one. It should either be S by S square plus omega square, which is sine omega t, or you should get this one. This is cos omega t's Laplace transform. So you should either get this or you should either get this. But here, I'm not getting that over here. You see, here you can see it is A2 into S square by omega square. So what I will do is I will convert this form into this form. Okay, that's what I said in the beginning of this class. That is, you need to learn to convert every denominator into a format which you recognize. So here, this will become A1 into S by S square plus omega square plus A2 by omega into omega by S2 plus omega square plus B by S plus R by L. Okay, this is how the equation looks like. So now you can find the Laplace inverse. Therefore, I of t is nothing but A1 into the Laplace inverse of S by S square plus omega square plus A2 by omega into Laplace inverse of omega by S square plus omega square plus B into the Laplace inverse of 1 by S plus R by L. Okay, this is how we find. So you get A1 into, what is the Laplace inverse of this? It is nothing but sine omega t. It's not sine, it is cos, I think, right? Cos omega t. The Laplace transform of this is cos omega t, I believe, right? Yes, the Laplace transform of this is cos omega t, okay? Not sine, just cos omega t. The Laplace transform, I made a mistake, okay? It's Laplace transform, this is cos omega t plus A2 by omega. What is the Laplace inverse of this? It is sine omega t. So this is u of t. Sorry, it should be u of t. It should be A1 cos omega t u of t plus A2 by omega. The Laplace inverse of this is sine omega t u of t plus b into, and the Laplace inverse of this is e raised to minus r by l t u of t. Okay, again, this is just a framework of how to find the corresponding values of whatever they are asking in the question. That's all. Okay, I just want to show you the general framework. This is for an RL circuit. Likewise, we also have an RC circuit and RLC circuit, which I won't take that much time to explain, because now I have already given you the framework of how to do these problems, right? Therefore, what you need, the most important thing of all, is that you need to find the general equation of the current or the voltage across whichever the element they are asking in the question, and then you substitute the value of V of S depending on the value of V of t that they have given in the question, and then by applying the Laplace inverse you find the corresponding value of whatever they have asked. That is how we do these questions. Okay, so according to your syllabus, the voltage signal, like I said, the voltage signal can either be a unit impulse signal, it can either be a unit step signal, or simply a step signal, or it can either be a pulse signal, or it can either be an exponential function, or it can be a sinusoidal function. Okay, it can be any one of these. Okay, here this Laplace transform, this is actually it's omega, no, okay, not S, it is omega by S square plus omega square. Okay, so these are the ways they will ask the problems. These are the ways they will ask the questions, right? So likewise, same way for RC and Rlc circuit also. Okay. Now in the same way, next we have is the RC circuit. Okay, so we are going to apply the transient analysis of RC circuit using Laplace transform. Okay, so here also the circuit, the circuit is pretty much similar. It is same like the other one, and this is an RC circuit, which means it consists of a resistor and a capacitor, and I'm going to take it as a series RC circuit with a voltage source called as V of t, a current generating a current I of t. The value of this resistor is R and the value of this capacitor is C Faraday. Okay, so like that we have R and C over here. So now I'm going to apply the Laplace transform to this equation. Okay, but before applying, I need to discuss about the initial conditions, and just like before, the initial conditions are 0, assuming that the initial conditions are 0, and also just like the other circuit, the switch opens at time, the switch closes at time t is equal to 0. That means before t is equal to 0, the circuit is in the off state, and after when the switch is closed, the circuit will start working. Okay, so here what we're going to do is now, so since the initial conditions are 0, right, we all know that the Laplace transform of a capacitor, right, the transformed impedance of a capacitor is a impedance having a value of 1 by Cs along with a positive voltage whose value is V of 0 by S, right? So right now here in this case, since the initial conditions are 0, the voltage will be 0. So therefore we are left with nothing but a simple Laplace transform with a voltage source V of S, capital letter V of S, where V of S is the Laplace transform of V of t, and then the switch is closed, so I will close it over here, and there is a resistor. The Laplace transform of a resistor R, it's R itself, but the Laplace transform of a capacitor will become an impedance whose value is 1 by Cs. Okay, if you all remember, it is supposed to be a capacitor with a positive voltage, right? This is actually the transformed impedance of a capacitor, right? The transformed impedance of a capacitor. But here in this case, since the initial conditions are 0, then the V of 0, which is the initial voltage across a capacitor or the initial charge across the capacitor, becomes 0. So therefore this becomes 0, so this will get shorted. That is why only a capacitor remains, so we will call that as 1 by S. And the current through the circuit, you are calling it as I of S. Okay, just like same like an RL circuit, then the procedures are exactly the same. Okay, so just like that, applying Kirchhoff's voltage law in this equation, you get the equation as V of S is equal to I of S into R plus 1 by Cs. Okay, the same thing, right? No, there's no difference over here. And likewise, I can now say that the current I of S is given by V of S by R plus 1 by Cs. Okay, and just to make it into a meaningful Laplace transform, because here you see you cannot simply apply Laplace transform having a denominator looking like this, right? Because if you look at all your Laplace transform formulas, the denominator will either be s plus a, or s square plus omega square, or s square minus omega square, or s plus a the whole square plus omega square, like that. So you can't express it in this format. So what I do is I make a symbol change over here. I say it becomes v of s by taking the LCM. This will become, let me see, RCS plus 1 into CS, right? Taking the, actually it's RCS plus 1 by CS, the CS comes on the top, so this will become into CS by RCS plus 1. And then what I do is I take RC is common. So if I take RC common, I get V of S into CS by RC into S plus 1 by RC. Okay, this C capacitor and this C capacitor cancel each other, and you will be left with this value, that is nothing but 1 by R into V of S into S by S plus 1 by RC. See, now this is in the form of one of the Laplace transform formulas, right? That is S plus A. If the denominator is in S plus A, 1 by S plus A, the inverse Laplace transform 1 by S plus A is e raised to minus at u of t, right? Like that. So now everything is just exactly the same like before. So the reason why we are focusing find the current is because once if you find the current, then you can find the voltage across any element. If you want to find the voltage across the resistor, just like the same in the previous RL circuit also, voltage across any element, to know the voltage across any element, you need to know the current across that element, and you also need to know the impedance of that element. That's all. So voltage across a resistor is equal to I of S into R, Ohm's law, right? I of S into R. This is the voltage across a resistor alone. Okay, and what is the voltage across a capacitor? Voltage, let me just write the full form of this. Okay, let me write the full form. Voltage across the resistor is I of S into R. But what is I of S? This is I of S, that is 1 by R into V of S into S by S plus 1 by RC into R. So maybe these two R will cancel each other, right? So therefore you will get as V of S is equal to, voltage across the resistor is now equal to V of S into S by S plus 1 by RC. Okay, so now what you need to do is you need to simply substitute the value of V of S. Okay, same way, voltage across the capacitor. Forgive my handwriting, I'm writing very fast, so because if I write too slow then you might get bored with this video, that's why. So voltage across this capacitor is the current through the capacitor, which is naturally it is I of S, and the impedance across the capacitor, which we all know it is 1 by CS. So this is the voltage across the capacitor, and we all know what is the equation for I of S, right? The equation for I of S is equal to V of S into S 1 by R into V of S into S by S plus 1 by RC, okay, into 1 by CS. If you look over here, this S and this S will cancel each other, and you will get 1 by RC into V of S by S plus 1 by RC. This is the voltage across the capacitor. So depending on the question, you will be either be asked to find the current through the element, or you will be asked to find the voltage across a specific element. Okay, if it is a current you want to find, then you need to find the current. If it is a voltage across any element, you need to find the current and multiply it with the impedance. And if it is the capacitor voltage you want, then you need to find the current, and then you multiply the current with the impedance. And in all these cases, you have to substitute the value of Vs, and just like before, the value of V of S depends on the value of V of t, which they will be given in the question. That is, the V of t, just like before, the V of t can either be del of t, or V of t can either be u of t, or it can either be a into u of t, right? Or V of t can either be equal to a pulse signal, okay, a pulse signal, u of t minus a, where this small letter a is the duration of the pulse, okay, assuming that the amplitude of the pulse is 1. If the amplitude is not 1, then you still have to multiply a constant called as a, where a is the amplitude of the pulse, and that is v of t. And likewise v of t can also be an exponential signal, right? It can also be an exponential signal, or v of t can also be a sine signal, okay. It can also be a sine signal. It can be any one of these signals, okay, depending on this type of v of t, we substitute the value of v of s. If the value of v of t is del of t, then we substitute v of s as equal to 1. If the value of v of t is u of t, we substitute the v of s as 1 by s. If the value of v of t is equal to a u of t, this is unit step signal, this is a step signal, which means the amplitude. This means this a u of t means it can be 3 u of t, or it can be 5 u of t, or it can be 2 u. A DC voltage, a battery, a DC voltage, okay, a DC voltage. So what is the name of this signal? This signal is called as 5 u of t, okay. That is what it means, okay. So in that case this will become, this is v of s over here is 1 by s, but here v of s becomes a by s, right? Or in this case it is 5 u of t, so it will become 5 by s, okay. Same way over here also, v of t represents a pulse signal, so the v of s is equal to 1 by s minus e raised to minus as by s, and the v of s over here is here v of t is e raised to minus 80 u of t, so applying the frequency shifting theorem, this will become 1 by s plus a. Here v of t is equal to a sin omega t, so therefore the equation becomes, the Laplace transform of this is nothing but a into omega by s square plus omega square, okay. This u of t is being multiplied over here just to show you that this is a unilateral Laplace transform, that is the integral is from 0 to infinity, okay. That's why we always usually multiply our answer or your signal with u of t. So basically the procedures are all the same, so all you need to do is substitute the value of v of s over here, and the rest of the procedure is exactly the same. That is, you, after substituting the value of v of s over here, then we try to find the inverse of the Laplace transform, and you find the inverse by applying the partial fraction method, okay. That's how we do this problem, okay. That is about the transient analysis of RC circuit. Now next we will talk about the transient analysis of RLC circuit, okay, and then we will move on to the problems. So next here is the transient analysis of RLC circuit, and here the circuit consists of a resistor, inductor and capacitor, okay. All three elements are present, so therefore the circuit will be as usual. It has a switch in which it closes at time t is equal to 0. It has a resistor, it has an inductor, and it has a capacitor. This is a series RLC circuit, okay. A series RLC circuit means has an R, an L and a C in series. And here you have the voltage source whose value is V of t, and this is the circuit, okay. Everything is just the same. Here you have R, the resistor is R ohms, here the inductor is L Henry and the capacitor is C Faraday. And this V of t generates a current called as I of t, and this switch and this closes at time t is equal to 0, and that's it. This is the circuit, okay. And now everything is just the same. Here also what we do is we apply the transformed equation over here, and the switch closes at time t is equal to 0 as usual, and also I'm going to assume that all the initial conditions are 0. Assuming that the switch closes at time t is equal to 0 and the initial conditions are 0, okay. So in that case, what happens if they have specified the initial condition? So what happens if there is a steady state condition? If they have asked it, then you have to consider that also. We'll be doing problems even with using steady state conditions. That's also very important, okay. how to understand whether the circuit is in steady state condition or not. You see, for that you have to read the question. In the question they will specify when is the steady state condition. Sometimes the steady state condition is when the circuit is open, or when the circuit is closed. So you should first read the question, understand it, and find out where is the steady state condition. The reason why you are finding, remember that, the reason why you are finding the initial conditions is because so that you can find the value of the initial current of the inductor and the initial voltage of the capacitor. Okay. But here, since I have assumed that all the initial conditions are 0, then the values becomes very easy, right? Then in that case, the Laplace transform of a resistor is R, the Laplace transform of an inductor is Ls, and the Laplace transform of a capacitor is 1 by Cs. Okay. So therefore, this is the circuit at time t is equal to 0. That is, at time t is equal to 0, comma, this is your voltage. This is the switch is closed at time t is equal to 0. So therefore, this becomes a short over here. And this is a resistor and an inductor and a capacitor. The inductor does not have a negative voltage in series to it because the initial conditions are 0. And the capacitor does not have a positive voltage attached to it because the initial conditions are 0. In both the case, the reason is because the initial conditions are 0. And this is your circuit. Here the impedance is R, here the impedance is Ls, and here the impedance is 1 by Cs. Therefore, the total impedance is R plus Ls plus 1 by Cs. Okay. And here you have the, not V of t, it is V of S. The Laplace transform. This is the Laplace transform of the circuit, right? So it is V of S. Okay. V of S. So now again we are going to apply the Kirchhoff's voltage law to the circuit. So therefore the equation becomes like that, is V of S is equal to I of S into R plus Ls plus 1 by Cs. Okay. Again we find that the equation for I of S is equal to V of S by R plus Ls plus 1 by Cs. Okay. So now again we take the LCM of this. So taking the LCM, what will happen over here? This will become V of S by LCS square plus RCS plus 1 by CS. That CS will come on top into CS. There you go. Okay. I want to make this into, but I told you, you need to make this into a form which you can understand, right? So what we do here is, see, this is what you need to understand. It is like I said in the previous for an RL circuit. It is, if you remember, the coefficient of S and S square and whatever the equation is, the coefficient all is exactly 1. So make sure you get that over here. In all these Laplace transform equation, try to make the coefficient of the highest degree of S to be equal to 1. So if I want to make this coefficient over here to be 1, what I do is I take the LC common. So by taking LC common, what happens over here? This becomes V of S into CS by, so I'll take LC common. So after taking LC common, this becomes S square plus, and over here we have taking C common, and if I L comes R by L, so it becomes R by LS plus, and here if I take LC common, it becomes 1 by LC. There, this is the equation. Okay. I'm not going to, in the textbook version and all, they actually went more further than this. They actually found the roots of this equation. You don't have to do that because everything now depends on this equation, because it's much more simpler once if you substitute the value of R and L and C over here. Okay, that is why I'm not moving forward with this. It's simply a time consuming process. So the actual problem is much more easier than the derivation itself. Okay, that is why. This is just to give you a framework of how the questions will be asked. Okay, so this is how the equation will looks like for an RLC circuit. Okay, granted, one thing is that this will be much more complex than the other two, because here all three elements are present, right? So that is one thing we need to address when we are dealing with an RLC circuit. That is, it takes some more time, and also you need to you need to learn to factorize it, which means you also need to be able to factorize an equation which you won't be able to directly factorize it. So that is kind of a problem when it comes here, because the main problem arrive over here comes when you're trying to find the inverse Laplace transform by partial fraction method. The method is very easy. Understanding the method is very easy, but what you need is the practice of finding the value of the coefficients very fast. You can't spend too much time on that. It is the time consuming process. The entire equation, this transient analysis of RL, RC and Rlc circuit, I'm saying the most time consuming process will be finding the value of the coefficients. But once if you learn some of the tricks of finding, which I'll be covering in the video, I'll be teaching you some of the ways of finding the inverse Laplace transform in a shortcut method. That is, I will be teaching you how to factorize an equation which you cannot factorize, directly factorize. I'll be teaching you that, okay? I will show you how to do that. But so here factorizing will be very difficult over here, because here the value of R and L and C are not given. So it will be very difficult, okay? So anyway, I'll be pausing my answer with this, okay? And of course, the voltage across, we all know now, from here I can tell you the voltage across a resistor, right? That is also where I will also show to you. That is the voltage across every element. The voltage across a resistor is equal to I of S into R, where I of S is the current through the resistor and R is the impedance of the resistor. Okay, so therefore I of S is equal to, again I of S is equal to, here I forgot to say, here C and C cancel each other. Okay, so I of S is equal to V of S into S by L into S square plus R by L C plus 1 by LC, okay, into R. So we have the equation as R by L into V of S by S square plus R by LS plus 1 by LC. All right, this is the equation. This is the voltage across the resistor, right? And the value of V of S depends on the type of the voltage signal, where that again depends on the type of the question. Okay, this is the circuit, this is the voltage equation, and the voltage across the inductor, is equal to the current through the inductor multiplied with the impedance across the inductor. And the value of I of S is, again, it is V of S into S by L into S square plus R by LS plus 1 by LC into LS. L and L will cancel each other, and you will be left with V of S into S square by S square plus R by LS plus 1 by LC. Okay. For those of you who are finding this partial fraction method slightly difficult, please don't hesitate to contact me. Okay, I will teach you how to find I will teach you separately how to find the partial fraction. Okay, it's basically just a simple thing, but when it comes to some tricky situation, you need to apply some tricky methods to find the values of the coefficients. Okay, so this is one of the equation over here. Again, the value of V of S depends on the value of V of t. As V of t can either be a unit step signal, it can either be a step signal, it can be a unit impulse signal, or it can be a pulse signal, or an exponential signal, or a sinusoidal wave. Okay, so this is it. This is the voltage across the inductor. Okay, and then after substituting the value of V of S, we find the inverse. Okay, we find the inverse using partial fraction method. We find the coefficients, and then we find the inverse of the values. That's it. That's the answer. So this is the voltage across the inductor. Next will be the voltage across a capacitor. Okay, and here the voltage across the capacitor is the current across the capacitor into the impedance across the impedance of the capacitor, which is 1 by Cs, and this is equal to, and the current through the capacitor is V of S into S by L into S square plus R by L S plus 1 by LC into 1 by Cs. Okay, and S and S will cancel each other, and you will be left with V of S here 1 by LC into V of S. Okay, I hope it's correct. S square plus R by LS plus 1 by LC. Okay, and from here we find the voltage across the capacitor. Okay, then after this, after substituting the value of V of S, we apply inverse Laplace transform using partial fraction method, and then we find the value of V of t. Okay, so this is how the question will be asked. The question can be asked in any format. Okay, they can give you any voltage, input voltage signal, and then they will ask you, then they'll give you a circuit. Alright, it can be an RL circuit, Rlc circuit, and that circuit might either have a steady state condition or does not have a steady state condition. If they have not mentioned anything about the steady state condition, then fortunately you can assume that the initial conditions are all equal to 0. If they have mentioned about the steady state condition, or if they have mentioned anything about the initial conditions, then you have to consider the initial conditions. So then the circuit becomes more complicated. Okay, but still it will be doable, but it takes some just nothing, just extra voltage will just comes into the picture, that's all. Okay, so we'll be doing problems based on these things, all these things. Okay, if anybody have any difficulty in understanding any of these portions, please be free to